They had the blueprints, they had the factories. Yet despite all this, they still couldn't build it correctly. For the Germans, this was an unbearable humiliation, not because of the aircraft itself, but because they couldn't explain why it kept failing. They were experts in aircraft design. After all, they had spent the previous decade creating some of the finest flying machines in the world. The Ta-154's aerodynamics showed no obvious flaws, its engines were powerful, and its structural logic appeared impeccable. Yet, time and again, the airframes kept failing. When the cause finally became clear, it turned out to be something so mundane it never appeared in reconnaissance photographs, and no captured example could reveal it. It was something so commonplace it barely warranted a second glance on the shelf of any peacetime factory. Before we delve into this cause, it's worth paying proper attention to the Mosquito. In the late 1930s, Geoffrey de Havilland approached the British Air Ministry with a proposal that most sensible people would have considered professionally awkward: to build a frontline combat aircraft primarily from wood, and not just partially, but with wood forming the very core of its structure. Spruce was used in the nose, birch plywood for the fuselage, and a composite sandwich technique employed balsa cores sandwiched between outer plywood skins. The resulting structure was to be shaped and finished by master craftsmen, not riveted together by metalworkers. At a time when every serious manufacturer was shifting to all-metal, stressed skin monocoques, de Havilland was proposing to go in the opposite direction. The Air Ministry's reception was cool. The idea of a frontline wooden combat aircraft struck the establishment as regressive, a step back to a technology the industry had already surpassed. Genuine concerns were raised about structural integrity, moisture resistance, and whether a wooden airframe could withstand the stresses of combat flight without gradual degradation. Yet de Havilland's counter-argument carried a logic the Air Ministry found harder to dismiss than initially assumed. Britain faced a critical shortage of aluminium. Supply chains supporting British metal aircraft manufacturers were stretched to their practical limits, and the pool of skilled metalworkers was already fully committed. But Britain had something else: a world-class furniture and woodworking industry. It employed artisans who had spent their careers working with wood to levels of precision most industrial processes couldn't match. These workers hadn't built aircraft before, but they could. Their skills translated directly to the precision woodworking required for a composite wooden airframe. It took considerable pressure, a shift in military calculus, and several compelling demonstrations before the Air Ministry relented. When prototype W4050 took off from Hatfield Aerodrome on the 25th of November, 1940, piloted by Geoffrey de Havilland Jr. and flight engineer John Walker, the institution that had resisted the project for 2 years found itself witnessing something entirely unexpected. By February 1941, W4050 had recorded a speed of 392 miles per hour at 22,000 feet during trials, a figure not just impressive, but superior to the contemporary Supermarine Spitfire Mk2. An unarmed wooden aircraft was faster than the RAF's primary fighter. Resistance from the Air Ministry ceased. The production Mosquito that followed adhered to the same principles: a balsa core sandwiched between birch plywood skins, supported by a spruce framework, all shaped by cabinet makers and furniture workers redirected into the aviation supply chain. The finished aircraft was light, rigid, and aerodynamically clean, qualities difficult for aluminium structures of the period to match at the same weight. The wooden construction, dismissed as primitive, proved to be one of the most sophisticated structural solutions in military aviation. Operationally, what followed was almost unprecedented. In its first 600 bombing missions, only one Mosquito was lost. 1. Meanwhile, RAF medium and heavy bombers of the same era suffered losses of roughly 5 aircraft per 100 sorties, a rate that amounted, in human terms, to industrial-scale attrition of aircrew. The Mosquito flew higher than most German interceptors and faster than anything that tried to chase it. It served as a bomber, night fighter, pathfinder guiding larger raids, and long-range reconnaissance aircraft. Total production reached 7,780 airframes built in Britain, Canada, and Australia. Its loss rate across all roles remained consistently lower than any comparable RAF type. By 1942, the Germans had seen enough. Erhard Milch, responsible for German aircraft production, formally tasked Focke-Wulf in September 1942 with developing a twin-engine night fighter capable of intercepting and destroying the aircraft that flew over Germany with alarming impunity, and to build it from wood, as Germany's own strategic material situation came under comparable strain. The required composition was strictly regulated: 57% wood, 30% steel, and 13% duralumin. Kurt Tank, the brilliant engineer who had led Focke-Wulf's design department since 1931 and created the formidable FW-190, took charge of the project. A man intolerant of failure caused by incompetence, Tank's new aircraft was designated TAR-154, with TAR standing for his surname. The Luftwaffe nicknamed it Mosquito, perhaps as a nod to its rival or even a form of flattery. Indeed, the German aircraft bore clear structural resemblance to its British counterpart: two engines mounted ahead of a wooden fuselage, with an airframe largely composed of glued laminated wood sections. German intelligence likely had access to downed Mosquitoes and studied their construction in detail, grasping the general approach to such a design. Originally designated TAR-211, indicating intended Jumo engines, the aircraft was renamed TAR-154 when plans changed, though the Luftwaffe's nickname Mosquito stuck regardless. Tank's team worked intensively through 1943, and that year the V-1 prototype made its maiden flight under Flugkapitän Hans Sander. But from that point, the program began its slow, costly decline. V-1 crashed on the 31st of July, 1943 due to landing gear failure. Other setbacks followed. Prototypes V3, V4, and V5 also suffered structural failures, including landing gear collapses and stress concentrations in the wooden airframe that engineers couldn't satisfactorily resolve. On the 6th of May, 1944, prototype V8 suffered a catastrophic crash. An engine fire killed both crew members, pilot Otto and radio operator Rettig. It would be wrong to attribute all early failures to a single cause, though one problem would ultimately doom the entire program. The TAR-154 had genuine engineering challenges of its own. But by this point, material shortages were also taking their toll. On the night of 29 to 30 May 1943, 719 RAF bombers attacked Wuppertal. The force included 292 Lancasters, 185 Halifaxes, 118 Stirlings, 113 Wellingtons, and 11 Mosquitoes. The raid triggered a firestorm that destroyed roughly 80% of Barmen district in Wuppertal, killing around 3,400 civilians. Wuppertal was no random target. It was an industrial city of strategic military importance, home to chemical and synthetic fuel plants and vital supply infrastructure. RAF bombing doctrine in 1943 didn't require pinpoint identification of individual factories. The entire city was the target. Practically speaking, everything within the blast zone was considered a legitimate outcome. Among the buildings destroyed was a facility belonging to Th. Goldschmidt AG. The Goldschmidt plant in Wuppertal produced a phenolic resin adhesive called Tago film, a paper sheet impregnated with Resol phenolic resin, supplied in rolls and officially designated by the Rijksluchtvaartministerium as the bonding agent for the TAR-154 program. It was the sole producer of this critical component. When Barmen burned, so did Germany's supply of adhesive for its wooden aircraft program. Did British intelligence know this when selecting Wuppertal as a target? Available records offer no definitive answer. No verified source confirms that the Goldschmidt plant was specifically identified or that RAF planners drew a direct link between it and the TAR-154 program. The bombing was part of a broad industrial campaign, and the destruction of the Tago film factory appears to have been incidental to the larger objective. Evidence does not support intentional targeting. Yet the records do confirm that among the 719 aircraft over Wuppertal that night, 11 were Mosquitoes, a detail that almost demands pause. The very aircraft Germany was trying to copy paradoxically helped eliminate Germany's ability to produce viable adhesive for its copy. Whether anyone intended this outcome remains unknown. But what happened next is clear. After the Goldschmidt plant's destruction, the TAR-154 program had to find a replacement adhesive. The substitute they found was too acidic. To understand why this mattered, one must consider how a wooden airframe behaves in flight. A glued wooden structure is not static under operational conditions. At altitude and speed, the airframe flexes under aerodynamic loads. Temperature differences between ground level and operational altitude cause the wood to expand and contract. Engine vibrations and air turbulence continuously transmit stress through every joint. The adhesive bonding the laminated sections must withstand constant micro-stresses across every glued surface. It doesn't just provide rigidity, it mediates movement. A bond that performs adequately in static ground conditions may behave entirely differently under cumulative flight loads. An overly acidic adhesive doesn't fail immediately. Instead, the acid gradually degrades the wood fibers at the bonded surfaces, progressively weakening each joint over time. Externally, the aircraft appears whole and intact. The connection seems strong and reliable. But beneath this surface integrity lies an invisible, microscopic reality within the laminated sections. Degradation accumulates silently, like a stealthy illness, eroding joint strength until, at a critical moment, it can no longer bear the expected load. Then, without warning, catastrophic failure becomes inevitable and sudden. Several TAR-154 airframes disintegrated mid-flight, stark testimony to fatal structural flaws. Academic records, like an epitaph, state the outcome with stark brevity, leading to the breakup and crash of several TAR-154s. The consequence was the cancellation of the entire TAR-154 program. An engine fire, however fatal, is a comprehensible mechanical fault, one that can be diagnosed and corrected. But an airframe disintegrating at altitude signals a far graver issue to those overseeing the program, a fundamental compromise in the construction method itself, revealing that the aircraft cannot be trusted to maintain integrity under the very conditions it was designed for. By mid-1944, each completed TAR-154 airframe required a staggering 12,000 man-hours of labor, an extraordinary figure even before the adhesive problem arose. It reflected Germany's critical shortage of skilled aviation woodworkers, a gap for which there was no ready solution. The program was expensive, slow, and now produced aircraft with an irreparable defect in structural integrity. Cancellation was the only rational outcome. Herein lies what Germany missed, something that transcends the war, the aircraft, and even this specific program. When German intelligence examined captured Mosquito airframes, they saw wood. They could identify the species, spruce, birch, balsa. They could measure laminate layers, recognize the sandwich construction technique, and understand the geometry. They could, in effect, read the aircraft's blueprint. But what they could not see, analytically or otherwise, in a way that would yield practical insight was the adhesive binding those layers together. That adhesive was Aerolite. Aero Research Limited, founded in Duxford, Cambridgeshire, in 1934 by scientist Dr. Norman de Bruffner, specialized in aviation adhesives. The product used in every Mosquito was a urea-formaldehyde resin developed through years of meticulous materials research into how wood behaves under load, and how an adhesive could be formulated to work with the structural properties of the material it bonded, rather than merely filling the gap between surfaces. A properly executed Aerolite bond achieved a tensile strength roughly 3 times greater than that of spruce itself. The joint was stronger than the material it joined. Under stress, the wood failed before the bond did. This is precisely the design criterion you need in a structural adhesive, predictable failure mode, occurring in a material you can see and replace, not in the invisible chemistry holding the structure together. Aerolite used gap-filling hardeners containing formic acid, but at concentrations meticulously calibrated to achieve curing without damaging the wooden substrate. The formulation was the product of deliberate, targeted chemistry, not an approximate industrial process. It had been specifically engineered for bonding aircraft-grade timber and performed accordingly, under aircraft-grade temperatures, aircraft-grade cyclic loads, and with aircraft-grade reliability. Tego film, by contrast, differed in nearly every relevant respect. It was a resol phenolic resin rather than a urea-formaldehyde resin, applied as an impregnated paper sheet rather than a liquid compound. Under normal circumstances, when the Goldschmidt plant remained intact and the specified material was on the production line, it performed its function adequately. But when, following the raid on Wuppertal, a substitute entered production, the acid chemistry was improperly calibrated for the application. In a wooden glider, adhesive that falls outside its specified tolerances does not fail predictably or safely. Yet chemistry was only half the problem. The other half lay in the hands of the workforce. De Havilland's Mosquito builders knew aerolite through practical experience. Cabinet makers and joiners recruited from Britain's woodworking industry brought with them an intuitive familiarity with timber and adhesives, knowledge that translated directly into correct joint preparation, proper application technique, and precise control of the curing process. Knowing how to prepare a wood surface before bonding, how to manage adhesive spread thickness, how to read the material under varying humidity conditions, none of this knowledge appeared in technical manuals in terms readily accessible to intelligence analysis. It resided in the hands and judgment of the workforce. The transmission of this invaluable tacit knowledge occurred through systematic training and the accumulated experience of an industry that had been working with these specific materials and adhesives since 1934. The absence in Germany of a skilled aviation woodworking workforce stood as stark evidence of this gap. The British furniture and joinery sector, which supplied de Havilland's production lines, represented a unique industrial heritage with no direct German equivalent on a comparable scale. When the TAR 154 glider required 12,000 man-hours to build, versus only a fraction of that for the Mosquito, the discrepancy reflected a problem no set of blueprints could solve. It was rooted in deeply embedded knowledge held by a workforce that had performed this exact task, in this exact way, for years. Some knowledge cannot be conveyed through drawings alone. It is passed down through years of practice, through apprenticeship systems, through the accumulated craft intelligence of an industry that had done something one particular way long enough for it to become instinctive. Britain, unlike other nations, had been working with aerolite and its associated woodworking tradition since 1934. Germany, meanwhile, started virtually from scratch amid acute crisis, forced to rely on inferior substitutes. The situation worsened when the factory producing the most viable alternative was completely destroyed in a bombing raid. Whether the bombers understood the strategic significance of their target remains unclear. Meanwhile, the Mosquito continued its relentless expansion. While the TAR 154 program consumed 12,000 man-hours per airframe and lost aircraft to in-flight structural failures, the very aircraft it was designed to counter flew unimpeded over Germany, retaining the same operational freedom it had always enjoyed. The Mosquito's loss rate over its first 600 bombing missions, just one aircraft shot down, is among the most remarkable statistics in RAF history. By comparison, RAF medium and heavy bombers suffered losses of 5 aircraft per 100 sorties. The Mosquito's loss rate remained astonishingly low, below 0.2%. This was not merely a performance gap, it represented an entirely different category of aircraft, operating in a far less threatening environment. Pathfinder forces relied on the Mosquito for its exceptional speed and high operational ceiling. Raids on Berlin, the most heavily defended target in Germany, included Mosquito operations flown at altitudes and speeds that rendered interception by German night fighter crews nearly impossible. The Luftwaffe's available aircraft simply could not reach them in time. The aircraft specifically commissioned to close this gap never entered service in meaningful numbers. It literally disintegrated over Germany's own test ranges before it ever had a chance to prove itself. Total Mosquito production reached an impressive 7,780 airframes. The aircraft not only survived the war but continued flying well into the post-war era. Aero Research Limited, an unassuming firm from Cambridgeshire, had quietly operated in Dagenham since 1934, its name scarcely appearing in historical chronicles. Erhard Milch tasked Focke-Wulf with creating a German Mosquito. Kurt Tank's team, talented, well-resourced, and working from genuine captured examples, produced something that looked right and flew briefly before literally falling apart. The night fighter capability gap the TAR 154 was meant to fill remained open throughout the war's most critical phase. Every hour spent building an airframe eventually cancelled was an hour not spent producing aircraft the Luftwaffe could actually fly. They had the blueprints. They had the factories. Yet they still could not build it properly. The answer lay in aerolite, a urea-formaldehyde resin sold in a tin can, produced by a Cambridgeshire company most people had never heard of, founded by a scientist named Norman de Braunau 11 years before the war's end. Germany copied the Mosquito's form, its dimensions, material ratios, structural geometry, but failed to replicate the specific chemistry of its adhesive, failed to reproduce the craft knowledge of the workers who applied it, and could not withstand the loss of its own substitute manufacturer in an RAF raid whose strategic intent may or may not have been understood. While German engineers desperately searched for acid-based adhesive substitutes and watched their gliders disintegrate at altitude, the Mosquito flew unchallenged over Berlin. Built of wood, bonded with a compound delivered in a tin can, assembled by furniture makers repurposed for war, this quiet British triumph, absent from most history textbooks, had a very specific address: Aero Research Limited, Dagenham, Cambridgeshire.